Hi, I'm Hallie Redfern,
I'm Cassidy Brock.
I'm Aviva Myers.
I'm Donovan Kelly.
and we're the Electrochemical Bacterial Sensor Team.
We'll be using cyclic voltammetry, or CV, which is a type of potentiodynamic electrochemical measurement. The purpose of cyclic voltammetry is generally to study the electrochemical properties of an analyte in a solution. The first step in setting up our cyclic voltammetry experiment is to connect the AC adapter into the power outlet and into the wave now. The next step is to connect the USB adapter into the wave now and into the computer outlet. This is the cell adapter that is used as a cap for the cell chamber and attaches to the screen-printed electrode. From the small black box provided in the Wave Now setup, we pick a blue screen-printed electrode. These electrodes are relatively inexpensive and are therefore good for initial experimentation. When inserting the electrode into the cell adapter, it is important to insert the white section first so as to have the black print immersed in the analyte solution. We then use a small segment of stiff paper to mount the electrode by inserting it on the non-colored side of the electrode into the cell adapter. This is a solution of 10 millimolar potassium ferricyanide in 1 molar potassium nitrate. We added 10 milliliters of this solution into the cell. We now place the setup electrode into the prepared cell. Place the cell inside of a beaker to stabilize the cell. Then, using the cell adapter, connect the cell to the Wave Now. Make sure to screw in the ends tightly.
To download Aftermath, make sure to visit voltammetry.net/pine/aftermath/install.
And then
To download the software, click on the second link under Overview of the installation. Choose the most recent version of Aftermath and download the software. Once installed, click the Aftermath icon on desktop, which will bring you to a sign-in page where you can enter as guest. Once in Aftermath, you can click Cyclic Voltammetry under the Perform and Experiment section. However, we learned that after calling the Pine software company that you cannot perform the experiment until you have moved a permissions file within the software. In order to run the experiment, we had to take the flash drive that came in the Pine Wave Now setup and attach the permission file to the Aftermath software installed on the computer. The permissions file will be labeled .papx. We copied this file and then clicked on This PC, then hit C drive, then Program Files. Then find the Pine file and the Aftermath program and paste in the permissions file. An experiment can now be run on the Wave Now using the Aftermath program. Click on the cyclic voltammetry under Run an Experiment. We will use the Pine parameters, which includes 10 segments, an initial and final potential of 0 volts, initially rising, upper potential of 700 millivolts, lower potential of negative 500 millivolts, sweep rate of 100 millivolts per second, and an electrode current range of 200 microamps. Then click Perform. This is the final cyclic voltammogram, which looks similar to that of Hyman-Kissinger experiment. Unlike a linear voltammogram, the cyclic voltammogram has loops, the number of which is dependent on the number of segments entered in the parameters. In our case, we had 10 segments, which equates to 5 full loops, as shown here. After obtaining that data, we began experimenting with the sweep rates, changing the rate from 20 to 50 to 75 to 100 to 200 millivolts per second. The lower sweep rates took longer to draw the graphs compared to the higher sweep rates. In addition, the higher sweep rates seem to increase the electrode current range, as shown by the graphs that appear more stretched out. This is a cyclic voltammogram from the Hyman and Kissinger cyclic voltammetry experiment paper. They performed cyclic voltammetry on concentrations of potassium ferricyanide ranging from 2 to 10 millimolar in 1 molar potassium nitrate. Their results are similar to our own. Our general plan to create the electrochemical bacterial sensor is to line the screen-printed electrode with a film of polyethylene imine, or PEI, and top that with phage, or immobilized virus. The primary purpose of the phage will be to bind to E. coli, which will alter the electrochemical properties of the analyte that will trigger the sensor. Over the course of the next 2 weeks, our plan is to run cyclic voltammetry on acetaminophenol, which is found in children's Tylenol syrup. This experiment will allow us to compare the concentration we find using cyclic voltammetry with the actual concentration found on the back of the packaging. In addition, we are planning to use HPLC analysis as comparative data to the cyclic voltammogram.